Hello, everybody. Thanks for joining me. Are you ready to talk about storage? Yeah, storage. So in the book, the title is a bit longer. Why software-defined storage is critical to your IT strategy, but I've shortened it here. Why software-defined storage matters. So by show of hands, who here in the room is familiar with software-defined storage and maybe could define it if they had to? Keep your hands up if you could define it. I'm not going to call on you. Okay, interesting. All right, that's a lot of hands for software-defined storage. That's good. I'm going to try to tell a story about the storage industry and what's happening and what's changing. And that story begins by talking about this data explosion. Usually, I see lots of nodding heads in this part because everybody's familiar with the fact that we have so much more data today than we can ever deal with. There are a lot of things driving this data explosion, starting with web, mobile, social media, and cloud. We're taking pictures every day. We're taking pictures of cats and food and our kids. And it's absolutely unacceptable if 10 years later that picture of that lasagna is not available the moment that we need it. We're talking exabytes of pictures of just lasagna, probably. These digital assets are growing because web-scale services like Facebook, YouTube, Netflix are growing in prominence. And consumers expect this readily available storage, and they expect it to be infinite. Video-on-demand services, things like Netflix. If you really want to watch your Game of Thrones or House of Cards and you hit the play button and 10 seconds later, if it doesn't start playing, you're like outraged and your night's ruined. At least I'll speak for myself. I expect it to happen immediately. Media and entertainment, the production process is incredibly stressful on a storage infrastructure. You're talking about lots and lots of information, gigs and gigs and gigs per frame of a movie, billions of frames that get made every year. So companies like Disney and Sony Pictures spend a lot of money on storage infrastructure, and it's just a staggering amount of content. Things like the medical industry also have vast imaging needs. They have to keep medical records forever. They have to keep x-rays forever. And you have regulatory requirements that make it even more difficult. So if you're in any of these industries, you're very familiar with this data explosion. There's just simply more data now than there ever has been before. I'm making it hard on the videographer. I'm walking back and forth. This is good. So the issue with this is that there's kind of there's a problem here, right? It's creating a bunch of challenges. First, challenges around capacity, scalability, and cost. We want to store more data than we've ever stored before. We want it to cost less than it's ever cost before. We want to be able to scale it up and scale it down immediately, instantly, with no drama, and have complete agility. That's the first challenge, is that this is the expectation today. Also, there's this demand for unprecedented agility. It's not just being able to access data from my workstation at my office. I want to be able to access all of my data from anywhere, at my house, on my mobile device, anywhere, anytime, on any device. It needs this agility that you can't get with many proprietary or traditional storage solutions. Also, especially now, people are demanding flexibility to store your data in your own data center or in the cloud, or move it back and forth between the two. This is a flexibility that we need today, and we just accept as being required. And also, a lot of people don't consider this, but once you start having petabytes and petabytes and petabytes of data, how do you know that all of it is durable? Right? It's taking this. You have systems that take the data and spread it out across a bunch of systems, and you're keeping extra copies of it to make sure that if you lose a copy, you can recover. And when you're talking about very large-scale storage systems, the technology that exists to make sure that your data is durable gets exponentially more complicated. So data protection is very difficult at large scale. These are challenges that I'm sure everybody can agree we have with data today. And the big issue with all of this is that there's a mismatch between IT storage budgets and the amount of data growth that we're seeing today. This sort of gray square here represents your IT storage budget. It grows roughly linearly, a couple % every year by the research that we've done. But the data is growing exponentially. And I don't know if you personally have encountered this little intersection point yet or not, but if you haven't, it's in the mail. It's coming. If you haven't hit it yet, you're going to. And that's the point where your IT budgets are not sufficient to cover the additional data that you have to store. A lot of people will say that, well, hard drives are becoming more dense, and that's going to solve a lot of this. Well, some of it. It's not going to solve all of it. The dollar per gigabyte decline is slowing a little bit. You need more than just larger, more dense hard drives, you need new types of hardware and new types of software to close the gap. This is sort of the problem statement. So what do we do with all this data today? Where does it live? We're talking about these exabytes of data of cat pictures and x-rays, and where do they live? Well, the first place they live is in a proprietary storage appliance. This is where most of our data is stored today. You essentially go buy this single-purpose storage system. Under the covers, it's really just standard servers and media. Really, it's standard storage media. It's standard chips, standard servers. And on top, there's a layer of proprietary software that exposes, standards-based endpoints to users and management interfaces to admins. And this is generally a good solution. It hides a lot of complexity from the user. It also hides a little bit of flexibility from the user as well. This is what you get by having sort of an appliance approach to storage. It also means that there's some vendor lock-in. If you buy a giant storage appliance from one vendor and you need to have more storage, you're going to probably go back to the same vendor and get another appliance. And that means there's some amount of lock-in. And that lock-in leads to a pricing premium. The cost of this solution is generally more than the value of its constituent parts. And that's really difficult to sustain over time, especially as more and more pressure is put on people to store more and more data for less and less money. So this is one approach. This is the traditional approach. Convenient, but generally inflexible. Some economic problems at the very, very large scale. The second way people store their data, and it's kind of funny, this slide looks very similar to this slide, but this is a totally different thing. Public cloud storage. The stack looks kind of similar. This is something like Amazon S3 or Microsoft Azure File Service or something like that. And really, it's the same thing, standard servers and media with a layer of proprietary software, generally based on Linux these days, that expose cloud storage APIs and management interfaces. It looks very simple. And again, complexity is hidden from the user. Flexibility hidden to some extent. The pricing is pay-as-you-go, which is very attractive for some people. You invest as your business grows, which makes sense. Public cloud storage is the fastest growing segment of the storage market. If you look at IT budgets and where they're growing, this is it. And it's mostly secret sauce above. So again, we're looking at kind of a black box where you don't really know how it's built. You consume it as a service. It's an abstraction. And whether the abstraction is exactly what you need it to be depends on your workload. But this is another place where a lot of data is going today. The issue is that a lot of these solutions aren't as flexible as they need to be to cope with modern workloads. I like to use this metaphor to describe how a flexible storage system should be. A lot of traditional storage systems behave like a whale in your data center. When you buy them, that is pretty much what they are until the end of time. They're that size, they're that shape, they do that thing, and that's it. What a lot of people, everything else you see in the data center behaves in a different way, though. It behaves more like a school of fish in the shape of a whale. Right? So it looks like a whale, it's the shape of a whale, but it's not made up of one piece, it's made up of a bunch of different pieces, right? Like, we all have multiple servers that work together in a distributed way. Storage doesn't typically behave that way, and we think that it should. So again, also, if, let's say, I have, following the metaphor, a storage system that's made up of a bunch of fish, right? And I lose half of them, what do I have? I have a smaller school of fish in the shape of a whale. It's still a school of fish in the shape of a whale, it's just smaller. If I want a bigger one, I add more fish, right? As opposed to this, where if I have a disease come and eat half my whale, I've got a dead whale. And it's this monolithic approach, right? And flexibility is everything for today's storage needs. It's absolutely everything. Being able to expand and contract and sort of make things bigger in place and avoid migrations and things is just critical. So I find this is a good tool to use when judging a storage system. Does this behave like a whale or a school of fish in the shape of a whale? So as a result of all of this data storage shortfall and data explosion, organizations are generally rethinking storage. I think this is pretty universal. People are thinking, oh gosh, something's coming up soon. I need to start planning for it now. I need to look at new storage platforms, figure out what's next. I need to be looking at using my hardware more efficiently, using hardware that's better suited and better tailored to my workloads. And also, I want more flexible utilization of the services that I deploy to solve these storage needs. So the organizations are spending a lot of time now rethinking their approach to storage. And that thinking about storage is happening in a broader context as well. Just to sort of pop back up to 30,000 feet and look at the data center in general, there's innovation happening at almost every dimension in the data center. If you look at how software is developed, it used to be waterfall, right? And then we started having more agile methodologies and XP and things like that, whatever. And then now we're looking at DevOps, right? Where it's full integration of operations and development together, right? Application architectures used to be monolithic, and then they became, N-tier, and now we're looking at microservices-based architectures for our applications. All the way down the line. Bare metal led to virtual services, leads to containers, etc. The same thing is happening with storage. Storage used to be a scale-up problem, and then it increasingly became a scale-out problem, and now we're looking at a software-defined storage technology category that lines up very well with hybrid cloud containers, microservices, and DevOps. Now, a lot of folks will sort of move the ball forward on every other dimension in their data center, and they'll leave storage for last because it's convenient and it works. It whirs in a corner, and I put data on it. And so they'll think, well, I really need to advance my application architecture strategy and my development model and everything else. And then they'll get to the end and they'll realize, I'm using this with old storage that it isn't as flexible as all this other stuff that I'm doing. So it's important to think of storage in the context of the entire data center. So what is software-defined storage? We all raised our hands when I said, does everyone know what software-defined storage is? And when I said, who can define it, a lot of hands went down. And I think that that's because a lot of people have different definitions. It's kind of funny. I'll share this anecdote with you. We've been doing a lot of research lately, talking to a lot of CIOs about what they think about storage. And I've heard this multiple times from CIOs. They'll say, I can't explain to you what software-defined storage is, but I know I'm getting it from EMC. I've heard that multiple times, right? And that's difficult for me to hear because the way we define it is very different from the way that they define it. So I'm going to talk about how we define software-defined storage, and let's see if it resonates with you. If you hear something that doesn't resonate with you, raise your hand, call me on it, we can discuss it. But I think it's the combination of server-based storage and storage orchestration. So what do these two things mean? Let's start with server-based storage. Server-based storage is the use of software and standard hardware to provide services traditionally provided by single-purpose storage systems. So instead of buying, a proprietary piece of hardware that's function is just to provide storage, you build the same thing using open source software and standardized hardware. Looking a little bit more like this. Now again, it's the same equipment. It's the same kind of storage media. It's chips from your favorite chip manufacturer. It's all the same stuff, except instead of building it in silos, where I buy one storage appliance and then I fill it up, and then what do? Well, I got to buy another storage appliance and I fill that one up, and then I buy a third and I fill that one up. Now I have these silos of data throughout my organization. It's hard to copy stuff back and forth. It's really time-consuming. Instead of that, you have a single distributed cluster of servers that operates as one unit. This is server-based storage. It's using standard servers, standard storage media, to do what storage appliances used to do. Incidentally, this is what Red Hat Storage does, but I'll get to that later. Server-based storage tends to scale better. So let's use this as an example. Let's say I'm deploying OpenStack, just because it's a popular example these days. And I've decided to go the storage appliance route because it's more convenient, and maybe I have a storage team that takes care of it for me, and it seems like the easy path. And so I've deployed this storage appliance, and I start spinning up my compute nodes. 1, 2, 3, 4, 5, and they're all humming along nicely. Now I want a 6th compute node, but I've run out of space in my storage appliance. So at this point, I have to stop and go, all right, I got to get another storage appliance in here. Drive a forklift into my data center. Do I have enough power, et cetera? It becomes a big capital expense. And you end up having spending on storage that kind of looks like a staircase, as opposed to a server-based storage system where you can add storage nodes at the same time you add compute nodes and scale them up at a much smaller increment. It ends up being a bit more predictable. It ends up being a bit more flexible in how you scale. You can actually even converge them so your storage node and your compute node is the same node. That's something you can't do with a storage appliance, is scale them up at the exact same time. So virtualized storage, it just scales better. You don't end up with these big cliffs in your sort of spending trajectory. And analysts are tending to agree with us. This is a study that IDC did a while ago that showed the breakdown of storage that's shipped internal to a server versus external. So this bottom wedge is the number of hard drives that were shipped inside SANs and NASs, and this top is hard drives that were shipped inside servers. And it used to be that most hard drives, 60% or more, or about 60%, were shipped inside of SANs and NAS and other appliance-based things. And that's changing. Now, the majority of hard drives are shipped inside of servers, meaning that you need to have software to manage all of the storage across all of those servers. Storage, of course, has been growing at 40% per year. We've established that. And I think that it's showing that people are wanting to use more flexible storage systems. They want it to be in servers, closer to their workloads. So that's server-based storage. And that's kind of half of software-defined storage, in our opinion. The other half is orchestration, which is, and it's probably obvious, but the ability to provision, grow, shrink, and decommission storage resources on demand and programmatically. So instead of having to go into a server room and hit a button, at the very least, or rack something up or whatever, you have a new workload. You can programmatically, through an API, a web console, or a command line, spin up a new storage resource, and it's available immediately. We just did a panel this morning where a couple of our storage customers were talking about how they can provision storage for an application in minutes now. And that's really critical for them, as opposed to having to go provision a new storage appliance, have it ship and show up at the loading dock and all these other things. But it's because of this centralized orchestration. It's because everything is controlled with a single system that does full lifecycle management. Now, if you talk to some of the folks at EMC, their Copperhead and Viper product is essentially a storage orchestration system that is a single control plane for all of the products in their portfolio. We think that's halfway. That's centralized control, but not complete flexibility of the storage services underneath, because it's not entirely server-based storage. It doesn't scale the same way that servers scale. It doesn't converge with other applications, et cetera. So we think that's half the question. Software-defined storage is sort of a rising tide in the storage industry, showing that it'll be about a $1.4 billion market in 2019, which is up from a $500 million market in 2013. So it's growing. It's not the largest segment of the storage industry, but it's one of the fastest growing segments of the storage industry. And in fact, one of our research reports stated that between 70 to 80% of unstructured data by 2020 will be held in software-defined storage systems. 70 to 80% of unstructured data. And the way things are going, that's kind of like 70 to 80% of data, because most data is unstructured these days. Who's heard the term unstructured data versus structured data? Most of us. Okay. Structured data you would think of putting in Excel. Unstructured data you wouldn't dream of putting in Excel. It's good way to think about it. Also, by 2019, the prediction is that 70% of existing hardware-based storage products will be available as software-only versions. So the industry is moving in this direction. So why does it matter? Oh, first, before I go into why does it matter, anybody think that software-defined storage is something different than this? Cool. Awesome. Hey. Got it. Good. So that makes sense. So why does it matter? There's a couple of really important differences between the old way of doing storage and the new way of doing storage. And the first is that proprietary hardware is giving way to common off-the-shelf hardware. Instead of using specialized servers, you're using standardized servers. And that means that your costs are lower and your supply chain is standardized. Instead of going to multiple vendors to spin up a new infrastructure, perhaps you can even just go to one, to get all of your compute nodes and your storage nodes at the same time. Industry standard hardware is good. Standardization makes storage, I think, more convenient. It means that instead of going to a storage vendor and having your choice of 15 appliance models or 20, you can build whatever system you want. It's kind of analogous to another show of hands. I'm doing hands today. I don't know why. How many people use a Mac versus how many people who have built a... How many people use a Mac? Right? That's a lot of hands. How many people have built a PC? Okay. So why did you build a PC? Because it was cheaper than a Mac? Maybe, but not always. You can build a really expensive PC if you try. You build a PC because you have very specific needs for your hardware. I need this graphics card to run this game. I want to have, this much storage, and I can't get a Mac with that much storage. You want the flexibility. With software-defined storage, you can bring whatever hardware you want. You can bring a whole bunch of expensive servers and build a performance-optimized cluster. You can bring a whole bunch of cheap servers and build a capacity-optimized cluster. You can even start with one and slowly morph to the other, if that's what you want. But instead of having to choose from a limited selection of storage appliances, you can build the one that perfectly matches your workload. The formula is simple. If you have a cluster that's too slow, change your CPU to disk ratio to be more CPU heavy. If you have one that is not big enough, then shift it to be more disk heavy. I mean, it's all about the processor to storage media ratio. And it's easy to change it over time. You can start buying servers with more drive bays in them. You can also make clusters larger or smaller with zero downtime. And I think everybody understands why you might want to make a cluster larger, but sometimes I don't know, let's say you're a video game company and you're launching a new massively multiplayer online game, and when you launch it, it needs to have a giant storage infrastructure because it's really popular and you've done all this marketing. And then over time, the game wanes in popularity and has less and smaller and smaller storage needs. You can depermission half of that cluster and use it for something else. And that's not something you can really do with an appliance without a whole lot of drama. So industry standard hardware is really good. That's one of the reasons why this matters. The second reason is because what was previously a scale-up architecture is now a scale-out architecture. So instead of buying larger and larger machines, you're buying more and more machines. And this is, as we mentioned before, a way to increase operational flexibility. But there's another part of this story that a lot of people don't think about, and that's that generally storage appliances get slower the more you fill them with disks. Right? If you buy a storage appliance, you put one disk in it, it's going to scream. It'll never get faster. You fill it up with drives, it gets a little slower and slower and slower because that appliance only has so many processors in it. Right? And that processor to disk ratio is getting less and less favorable as you fill it full of drives. Right? So generally, they get slower the fuller you get. Software-defined storage clusters get faster when you make them larger because you're adding servers at the same time as you're adding disks. Right? So you can actually have performance that scales with capacity. And that's a difficult thing to accomplish, especially at the multi-petabyte scale. Of course, software-defined storage systems can also take advantage of a whole variety of different storage media, like flash technologies, persistent memory, new KV drives, that sort of thing, that allow you to really use it's like building a PC. You can use the latest and greatest of whatever comes out and make it part of your cluster and get that performance that you need that maybe isn't available in an appliance yet. But anyway, it's important to have performance that scales with capacity, especially at the multi-petabyte scale. The third reason that this matters is because hardware-based intelligence, these smarts that used to be locked in the hardware, are now in software. And let's face it, software is better than hardware. If you can implement the same thing in software versus hardware, you will always choose to do it in software. Always, because software is more flexible. Software fits in more places than hardware. It behaves differently than hardware. I can only think of one example of something that was hardware and got implemented in software and was worse, and that's a Win modem. I can't think of any other examples. But it leads to more programmability, agility, and control, and generally software is better than hardware. You can deploy software-defined storage systems on bare metal, of course, but also in containers, on virtual machines, inside the public cloud even. It can go anywhere that software can go. You can start on a single server. You can start on 1,000 servers. You can grow and shrink as you want. So software is more robust and more powerful. And then, of course, you're at Red Hat Summit, so this last one hopefully will resonate with you. What used to be innovation occurring in a conference room or on a conference call or on an internal mailing list is now happening on GitHub and on public mailing lists and in bug trackers where we think it should be. So because it's open source, you end up with technology that is more flexible, better integrated. And as an example of this, the Ceph technology has contributions from folks like Intel, folks like SanDisk, folks like Supermicro and Quanta, who help make sure that it runs really, really well on their hardware. And because it's open source, all these contributions have no barrier at all. Now, I would be a complete charlatan if I didn't make this point as well. Because I've been sitting here telling you how amazing software-defined storage is and how it brings all these benefits and everything. Well, it's not the only thing that you should consider. On the left side here, it really is a balance, and it's a dilemma that you have to consider for every workload. Appliances are super suitable for small-scale workloads. If you have an Oracle database or something that's tier 1, it's performance-focused, it's small-scale, and you don't have a giant storage team, an appliance just might be the thing for you. Like in your kitchen, a toaster toasts bread. Well, your gas stovetop will also toast bread, but it takes a little bit more skill. Sometimes you should just buy a toaster. On the flip side, software-defined storage brings this performance, and it brings economy at petabyte scale, and it brings durability, but it has a learning curve. This is not something you just throw in your data center and plug in and start loading with data. It's a distributed system. It behaves way more like BitTorrent than it does like a NetApp. And it's a peer-to-peer system that's complicated and requires you to be knowledgeable about systems and knowledgeable about DevOps. So if you want the benefits that software-defined storage brings, this flexibility, this economy, the ability to scale performance and capacity at the same time, it takes a bit of investment in learning how to operate these new systems. But we're all Linux folks in here, right? Yeah. So what can it be used for? Why does this exist? Well, I think the first answer to that question is, let's look at some of the superpowers. So a system like Ceph is a very interesting system. Everything you put into it gets split up into a bunch of chunks and sent across the entire cluster, and it's massively distributed. There's no large file sitting on some server that's only served by one spindle. Everything is distributed, which means that reads are parallelized, writes are parallelized. Everything's spread across a giant cluster. And that means that Ceph is particularly good at OpenStack. Say, for example, I put a virtual machine image inside of Ceph using OpenStack Cinder. What's going to happen with that VM image, it's going to get split into 4 megabyte chunks, and each of those chunks is going to be sent to a different storage server. So when I boot that virtual machine, it boots off of dozens or hundreds or thousands of hard drives, which means you get this parallelism on reads. It works to overcome the latency you introduced by having it be a distributed system in the first place. But it leads to one very important killer feature. You can take that disk image that's been spread across thousands of servers in Ceph and make a copy-on-write clone of that disk image without taking up any additional space, and you can boot a second virtual machine off that image. Once it starts booting and writing to its copy, it'll take up additional space, but not until then, and it happens instantaneously. You can do this on a lot of traditional storage systems too. You can take a virtual machine image sitting on a NAS and make a copy-on-write clone, and then when that second VM boots off of it, it's booting off of the same NAS as the first one. But because Ceph is massively distributed, when you make that copy-on-write clone and boot up a virtual machine, it also is reading from a distributed cluster. The upside is instantaneous parallel creation of VMs at scale. You can do that and make one copy. You can also make thousands of copies. Take a virtual machine image, copy it thousands of times. It happens instantly. You can boot up thousands of VMs, and all those reads are distributed. This is why a lot of people are choosing Ceph for OpenStack, and it's why a software-defined architecture like Ceph is so applicable to something like OpenStack. There's some conveniences as well, also that as you're serving these VM images, you can also do object storage, file storage, and database storage for applications running on top of OpenStack because it's a unified storage platform. It's got that flexibility. So to answer the question, what is it good for? Well, because it massively distributes data, Ceph is uniquely suited for something like OpenStack. It's a good example. Another sort of superpower of a system like Ceph is that it can grow to petabyte scale. We've talked about this. It can grow to petabyte scale with no single point of failure. Every part of the architecture scales out. Everything remains massively distributed. And that means that it can be a great solution for things like object storage. Object storage is sort of a recent movement in the storage industry. It's the result of people realizing that if I have a file system with billions of files and millions of directories, what's the purpose of having a hierarchy anymore? Obviously, some system's going to be managing that for me anyway. So object storage is like a big file system without the hierarchy. It's much flattened, and it's really good for storing unstructured data. So if you are downloading images from Flickr, they're coming out of an object store. When you do a Google search, I promise there's an object store involved in there somewhere because a file system at that kind of scale will just fall over. Because Ceph can grow to this kind of scale, it's a great solution for object storage. It works with industry standard APIs. If you want to build Amazon S3 on your own premises, Ceph is really good for that. It also spans multiple geographic regions. It has no single point of failure. And the distributed architecture of software-defined storage matches the distributed nature of the applications that consume object storage. So another place that's really useful is object storage. A third superpower, and this one I'm talking about Gluster, is that it can work in a lot of places. So software-defined storage can be deployed on hosts, VMs, private cloud, public cloud, hybrid cloud, spanning the two, synchronizing across the two, but also inside containers. Containers are super cool. They're very powerful. But when you shut down a container, all the data in that container goes away. You need a persistent storage layer for those containers. And it's even better if that persistent storage layer behaves the way containers behave. So a good solution for software-defined storage is containers, persistent storage to applications running in containers. What's really cool about this is that because software-defined storage is flexible, it can be deployed inside containers. Try putting a large storage appliance inside a container. It doesn't even fit. It doesn't even make sense. But software-defined storage can. So you can have a system where you have a whole bunch of servers that are running containers that are optimized for storage. Maybe they're really big servers, 36-drive servers, something like that, and they're optimized for storage. Then I can have a bunch of servers on the top here that are optimized for running applications. Maybe they have more processors, less drives, etc. But I can have servers in the middle that also run containers, that some of those containers are running storage and some of them are running applications. And I can move the line back and forth as needed. So if I have a workload that all of a sudden says, oh man, this article I ran is on the front page of CNN and now everybody's hitting it. I need to have, but it's not a lot of data, so I don't really need to have a lot of storage, but I need a ton of application servers. I can take some of these converged servers and make them application servers. If the opposite happens, I can make them storage servers. Being able to deploy software-defined storage within a containerized infrastructure means that you can sort of spin up and tear down containers at will to make your cluster larger or smaller, or your application servers larger or smaller. And as it turns out, storage, software-defined storage, generates about 10% overhead on these converged servers. So the net is that you can use these servers more completely instead of having a bunch of storage servers that are idle a lot of the time and a bunch of application servers that are idle a lot of the time. You can do both using containers to deploy them both on the same hardware and sort of make it elastic, where I can be application intensive today and storage intensive tomorrow. So containers are a really good use case for software-defined storage, especially because it can be containerized, it can be a storage backend for containers, and it can do so in a completely converged manner. So up to this point, I haven't talked at all about Red Hat storage. But obviously, we're here at Red Hat Summit, so I'll spend a little bit of time to talk about Red Hat storage. Because I'm doing the hands thing today, show of hands, who's worked with Ceph or Gluster before? A few hands. You should be at Sage's talk if you've worked with Ceph or Gluster before. That's good. That's good. Not everybody. So I can tell you something about Ceph and Gluster, which is good. We have two technologies in the Red Hat storage portfolio: Red Hat Ceph storage and Red Hat Gluster storage. They're based on Ceph and Gluster, which are two acquisitions. We acquired Inktank in 2014. I came from Inktank. In 2014, we became part of the Red Hat team, bringing Ceph along with us. A few years before that, Red Hat acquired Gluster Incorporated, bringing Gluster into the fold. And these technologies they're very similar. They have a lot of similar heritage. They're both completely software-defined storage systems, completely comprised of software. We don't sell hardware. They're share-nothing, scale-out architectures, meaning that there's no single point of failure anywhere in any of these architectures, and every component can scale out. These technologies also provide durability. So all the data that you put into them is completely durable. You can lose many of your servers and still be able to rebuild the data from the servers that remain. They're both self-managing and self-healing, so that when a server dies, you don't have to go get involved. It will just rebalance all the data across the servers that remain. And when you're talking about multi-petabyte clusters where there's thousands and thousands of servers, it's important that you don't have to do something when one of them dies, because one of them is going to be dying all the time. If you have tens of thousands of servers, one's going to be on fire at any given moment. The system can't fall over or require some kind of intervention. So they're self-managing and self-healing. And of course, they're supported by the experts at Red Hat. We are major contributors for both of these technologies. And again, they're open source software that run on top of standard hardware from our friends at Intel, Dell, Quanta Cloud, SanDisk, Cisco Supermicro, Fujitsu, and many, many other names. We understand that software-defined storage without hardware it doesn't do anything. We need hardware to run. So it's important to us that the hardware that our customers choose is optimized for use with both of these technologies. A lot of people ask, well, what's the difference between Ceph and Gluster? And it's actually kind of an interesting question, because architecturally they're very different. Ceph is fundamentally an object store at its lowest layer, and it has a block, object, and file interface built on top. Gluster is fundamentally a distributed file system at its lower layer. And the consequence of that is that, I'll put it this way, An object store is much easier to scale out than a distributed file system because an object store is a simpler thing. Objects are trivially parallelizable. You can take that work and split it across a bunch of servers in a really easy way. So the Ceph project chose to implement that first and build everything else on top of it. What results is a more robust but also way more complicated architecture. Whereas Gluster is a scale-out file system. So it went with a much more straightforward architecture. It's not as multi-layered, and it's really simple. You have a Linux server with some drives in it, and you add all those drives to Gluster. You add another server, you add those to Gluster, add a third server, just add those to Gluster, and you keep adding drives. They're called bricks, and you just keep adding them until you don't need any more. Very simple architecture. So as a result, Ceph is what we generally prescribe for large-scale infrastructure, for petabyte scale, big cloud projects or large object stores. And Gluster is what we prescribe for all of that software-defined storage that needs to be nimble. It needs to fit in small places and nooks and crannies like the public cloud. So this is sort of our map of how Red Hat storage products fit in all these different environments. So on the physical side, Red Hat Ceph Storage and Red Hat Gluster Storage are co-engineered with Red Hat Enterprise Linux. They run solidly on Red Hat Enterprise Linux. And so if you're running on bare metal, either one is an appropriate option depending on what you need and what your architectural priorities are. On the virtual side, we've paired Red Hat Gluster Storage with Red Hat Enterprise Virtualization. So if you're looking to have a storage backend for Red Hat Enterprise Virtualization that scales and stores your virtual machine images, we've paired Gluster up with that. And we've made that choice because Gluster is easier to hyperconverge, and people are looking to hyperconverge Red Hat Enterprise Virtualization with Gluster Storage. On the private cloud side, Red Hat Ceph Storage and Red Hat OpenStack Platform are what we've paired. And people say Ceph and OpenStack go together like peanut butter and jelly, and they really do. It's overwhelmingly preferred by the OpenStack community. About 60% of users polled use Ceph as their storage backend inside of OpenStack. And so that's what we prescribe as well for private cloud environments. On the container side, because Gluster is a more nimble storage technology, we prescribed it for use with OpenShift Enterprise. I think just yesterday we announced our container native storage vision, which is Red Hat Gluster Storage and OpenShift Enterprise paired together and tied together very closely. And on the public cloud side, Red Hat Gluster Storage and Red Hat Enterprise Linux work together very well inside all of the public clouds. So a lot of people will deploy a Gluster cluster inside one of the public clouds, and then they'll install one on premise, and they'll synchronize between the two. Again, not something you can do with an appliance. And because Gluster is nimble and malleable and embeddable, it's what we choose for the public cloud. So this is a bit of a roadmap of how it all fits together here at Red Hat. And of course, Ceph and Gluster are built on very strong communities of innovation. The Ceph project in particular is a very vibrant community. We get regular contributions from folks like Intel, from folks like SanDisk, from customers like CERN and users like Yahoo. We have Ceph days in cities all over the world. We've done dozens of them at this point. We'll do them in every local city we can find a venue in. We do quarterly Ceph Developer Summit events and that sort of thing. You'll notice that we have just a lot of traction here. 97 authors per month is the average, roughly. So 97 people per month work on the project. About 2,400 times a month, somebody thinks they've done something cool enough that they want to share it with the community. That's a lot. About 260 people actually are active on the mailing list every month. On the Gluster side, we see a community that's a bit more stable. It's been in market for a little bit longer, and so this is a community where we're seeing a lot of adoption right now. Over 11 million downloads in the past year for Gluster. So people are using it for all kinds of little convenient problems that they have. We've seen a lot of increased development velocity, a lot of increase in authorship, and man, there have been. It's funny, we haven't done a major release of Red Hat Gluster Storage since Red Hat Gluster Storage 3 a couple of years ago, but these point releases have been like major releases. That's like erasure coding and tiering have been introduced, replication's been introduced, bitrot detection, like major features have been introduced in the 3.1 series. We're at 3.1.3 now, no, 3.1. I always forget because we haven't done a major release, but these features have been hitting it forever, right? So we have a lot of development velocity on the Gluster side. It's a very active engineering team, and there's a whole lot of consumption. So I'd like to leave you with these two resources. If what I've said to you today makes you interested in checking out Ceph or Gluster and seeing kind of how they behave, these two URLs will provide the fastest way to get your hands on a Ceph cluster or a Gluster cluster. If you go to these URLs, fill out a few forms, we will set up Ceph or Gluster for you in Amazon Web Services. We'll give you the keys, and we'll pay the bill. And you can log in and start playing around with Ceph or Gluster and keep it as long as you like. Now, we'll also give you some curriculum. We'll give you about 6 hours worth of exercises that'll show you how to walk through all of the different features and see how these systems behave. So if you want a quick half-day just primer on Ceph or Gluster, these are the places to go. And with that, I thank you for your time and for your attention. I'm happy to answer any questions that you have at this point, but thank you.